Hello, thank you for choosing to do some physics with me here today. In this video, I'm going to follow up to my previous video where I talked about how we graph and some of the ideas behind graphing in physics and how I like to teach my students how to create their graphs so that we get a nice uniform graphs across the board for all of our labs. In this video here, I'm going to talk about what graphs tell us about the information that we can pull from our scatter chart, scatter plot graphs, and how we can use that then to further our lab investigations. So in this document here, I have 3 graphs that we're going to walk through. Each one has some slightly different information in it, and we're going to analyze the main couple parts of these graphs. So this very first one here, it's a little bit hard to see. It didn't copy over the greatest, but this is weight here. I can write this out. This is weight, and this down here is time. Hopefully you can see that all right. So this is weight and time. Weight measured in pounds, lbs, and time measured in weeks. We have a bunch of data on this graph here. You'll notice a couple things from the previous video where I mentioned kind of the 4 main things that we want to have on a graph. We want to have our axes labels for the X and the Y. So there's 2. So I have those. We want to have a best fit line. We're missing that. And we want to have a graph title. We're also missing that. But we're going to kind of talk about that information throughout what did the graphs tell us here? What does this graph tell us? So I want to build upon that. So the very first thing here, in order to analyze a graph, a scatter plot, we need that best fit line. The best fit line tells us the relationship that we're looking for. So our relationship here, our best fit line, I'm going to draw in one here. I know that this data, I created this data, so I know for sure that this all lines up about like that. I didn't do the best. Let's try that one more time. See if we can get that a little bit better. There we go. That looks pretty good. So this is my best fit line for this data. I hand drew this one in. Again, if you're using graphical analysis, it will automatically create that. From this best fit line, we're going to pull our math model. Our math model is what's going to allow us to make predictions of like way farther out, a lot easier, quicker than sometimes the graph can do, but also more accurate than what the graph can do. When we're dealing with a linear graph, it tells us that the math model is y equals mx plus b. Now, y in this case is not represented on this graph. Y is weight, or I'm going to do w. Because w, or weight, is the variable that's graphed on the y-axis. It is tempting for some people to do pounds, lbs, equals something, but pounds is the unit that represents weight. Weight is the variable. So weight equals m. M is the slope of our best fit line. So if I come back over here, let's pick a nice pink color here. This is a little bit of a review from algebra, how to find the slope of a line. We pick 2 points on our graph, preferably 2 points that we can kind of tell where about they are. This one looks pretty good to me. And this looks all right here. Actually, I remember the first point. We're going to do the first point. That one I can tell a little bit easier. You can pick any 2 points on your graph. It really doesn't matter. I'm just picking one that I think I can read the easiest in this case. Because again, it's a line. The slope anywhere on this line should be the same. So in order to determine the slope, I'm going to look at the rise over the run. Right here I have the rise, and then I have the run. Slope is rise over run. And it's often very, very tempting for people to, in this case, particular with graphical analysis, to look here and go, okay, there's 1 and there's 2. That's my run. And then my rise, well, I got about half here, 1, and then another half, so 2. Well, that's not exactly the case here because those boxes don't represent how many changes there are, how many weeks have passed for the run, or how many pounds have changed in the rise. So we need to look at the numbers here. So I'm going to say right here, I start at about 5, and then it looks like I go up to about 25. So my change there, my rise is 25 to 25. So my rise is 20. My run, I go from 0 over to 10. That one's right on the line. So I go from 0 over to 10. 20 divided by 10 gives me a slope of 2. So I can go ahead and put that in my math model. Now, one thing I mention a lot in my classes is that in science, the main difference between math and then science is that science gives math meaning, gives math purpose. Right? Math is a lot of theory, a lot of things going on, but then science, the application of math. We need to give things meaning. 2 by itself doesn't have meaning. We give things meaning by giving them units. So 20, my rise, is measured in pounds. So it's 20 pounds over 10 weeks. So therefore, my slope is 2 pounds per week. Okay. In my math model, I don't need to write that out, but it's important to know that my slope is the y unit over the x unit, pounds over weeks. The y unit, pounds, over the x unit, weeks, pounds per week. And we pronounce that pounds per week. Okay, so that's my slope. Now, the x variable, just like the y variable is w, I'm not going to write x here because x is not represented on my graph. I don't have an x anywhere here. What I do have is time. Time I'm going to represent with a lowercase t. That is going to be my x variable. Plus b. b is the y-intercept, or some people also call it the starting point from time to time, as another way to think about it. So on this graph, the starting point I've already kind of identified. We're looking at the y-intercept, the y value. So when x is 0, what number is it? It is 5. So I'm going to put that right there. So when this crosses, for me, it looks about 5. I made the data up, so I know for sure that it's 5. But based on looking at the graph, I can see that. Again, as we get further down, we look at the next example. Graphical analysis has done most of this work for us already. So that's our slope. So our y-intercept is 5. And again, we need to give that number a meaning, give it a purpose. It is 5 pounds. When time is 0, the y-intercept is 5 pounds. And so this is the numerical information that we can pull from it, but we can also start to think about, okay, what does this actually mean? What is this graph trying to tell us? Well, by looking at the information that we're given, we're seeing that we have an increasing weight over a certain amount of time. The weight starts small, 5 pounds, that's pretty light, and then starts to get bigger and bigger and bigger and bigger, heavier. At 30 weeks, we're over 60 pounds. You know, maybe this is the weight of a baby, right? Weight of a baby, maybe a really big baby. Most babies aren't going to be over 60 pounds at 30 weeks. But that idea, right, is we can see here that this is increasing weight. So we're kind of inferring what information we're being told here, right? How much weight that baby is gaining every week. Every week, this baby increases its weight by 2 pounds. Okay, so that's what the slope tells us. The slope tells us every week, the baby, we'll just call it a baby. I don't know. I made this data up. The baby gains 2 pounds. So the baby's getting heavier. The baby's growing. That's great. Now, what does the Y-intercept tell us? Well, the Y-intercept tells us when weeks was 0, when time was 0. Well, when would that be? Oh, well, that would be when the baby was born. When the baby was born, it weighed 5 pounds. So then from here, we have this information. We have a math model. With this math model, we can then make a prediction. I can see on my graph that, like, let's say 40 weeks right here. At 40 weeks, what's the weight of this baby going to be? Well, it looks like maybe about 85 pounds. It's kind of hard to tell based on my graph. But I could check that by using my math model. Let me get a different color here. Let's go green for this real quick. So if I want to know the weight of the baby after 40 weeks, well, then I just plug in 40 for t, my time, and then solve. 2 times 40 is 80 plus 5. The weight is 85 pounds after 40 weeks. So all this information I get from my graph shows me this, and then I can infer all of this information. I can pull all of this from my graph. The slope tells me that every week the baby gains 2 pounds. The Y-intercept tells me that the baby was born weighing 5 pounds. And then I can use that model to make a prediction or to know the weight of the baby at any given week, assuming it doesn't change at all, right? Considering that this model stays the same. So this is what a graph can tell us. Now let's take a look at the next one here, because I don't get stuck too long on one here. So this graph shows us the title. It says cost of a hotel. So great. So this is how much a hotel is going to cost based on number of nights. I see on the x-axis here. So the number of nights that we stay at the hotel, we're going to see the cost increase. So again, if you're using graphical analysis, you have this box on there, which tells you everything that you need to know. The math model is right here. So again, we start with that math model, y equals mx plus b. I have m and I have b given to me right there in my box, straight from graphical analysis. No need to do rise over run, anything like that. So my y variable in this case is cost. We're going to call that C here. So that is C equals M, my slope, 40, X, number of nights, we'll just call it N for now. That's fine. Something that makes sense with the data that we have, plus B, which is just 0. And I could actually just leave that off because it's 0. It doesn't matter. It makes no difference if it's there or not. If you really want to write it out, great, more power to you. That's totally fine. But because it's 0, we actually don't need it there. So my math model here is that the cost of the hotel is going to be $40 times the number of nights that you stay. So the slope in this case is going to be 40. But more specifically, we have to look at the units. 40, the Y unit, dollars, $40 per night, right? Think about the cost of a hotel or the cost of an Airbnb or whatever you're staying at, right? A rental, $40 per night. Every night that you stay there costs you $40. Now that might change. So you could make a different model here. Maybe there's a deposit that you have to put down. And so maybe it's plus $100. You have to pay $100 before you even stay, something like that. Okay, but for now, $40 per night. So that's what the slope tells us. The y-intercept tells us, well, in this case, it's simply the y-intercept is 0. So if you don't stay at all, let me change color here so it stands out. If you don't stay at the hotel, you don't have to pay. That makes sense, right? If you're not staying at the hotel, why would you pay for the hotel? You don't stay any nights, then you don't have to pay for it. That kind of makes sense. There we go. Once again, we could use this math model to make predictions. We could figure out what's going to be the cost of the hotel after 14 nights. We plug in 14 for n. The cost equals 40 multiplied by 14. And then we get our answer there. If you want to do that calculation real quick, you can. I'll do it on mine. There we go. Not super great at math in my head, but that's $560. And again, I want to make sure I put units on that. So that's another example there. Let's go ahead and scroll on down to one more. In this case, we have weight versus height. So we have weight on the side here. We're going to call that W. And then height on the bottom, we'll call that H. Once again, I'm given a math model of y equals mx plus b. So that's my base math model, the equation for a line. Y, the y variable, is W. So weight equals m, the slope. I can pull the slope right from graphical analysis, 0.7367. So in this case, this is one where the data is not, super nice, but that's okay. 0.7367 times x. X is our height. The x variable, again, not centimeters, but h. I can give that a little bit of space so it stands out. Plus our y-intercept. Our y-intercept, in this case, is negative 0.5963. So let's talk about what this means, what this information means for us. Let's pick a different color here. Our slope is 0.7367. Our units for that are rise. Our y unit is on top, pounds per. Our x unit, centimeters. So pounds per centimeter. So when I wrote up this data table here, I'm thinking about a lab where maybe a group of students measure their height and measure their weight and then create a graph. So as the students get taller, their weight increases. So that is what our data here tells us. So a student will weigh, will weigh 0.7367 pounds for every centimeter of height. So in theory, if a student knew how many centimeters tall they were, they could figure out their approximate weight. Or if they knew their weight, we could work backwards and figure out their approximate height. Now let's talk about this y-intercept. This one looks a little bit weird. It's got that negative out in front. So what does that mean? Well, in this case, the y-intercept is when the height is 0. So when height, the y-intercept is always when the x variable is 0. So in this case, the x variable is height. So when height is 0 centimeters, a student will weigh negative 0.5963 pounds. Now, if we really think about this, does that make sense? One, does it make sense for a student that has no height, 0 centimeters, no height at all? Does it make sense for them to have a weight? No, probably not, right? They have no height. They don't really exist, right? It's impossible for somebody to have no height. So if they have no height, they don't exist. If something doesn't exist, it shouldn't have any weight. If something does have weight, can weight be negative? No, that doesn't really make sense either, right? Things have weight. Weight is always going to be a positive number. In the grand scheme of things, weight is going to be what we call a scalar term. As a little, again, sneak peek there at things to come. Weight is a scalar. So it's a little sneak peek at a word there, scalar. So what do we do when we have something like this, where our y-intercept doesn't really make sense? Because I guarantee at several points during my class, during labs that we do and labs that I talk about, you will get data that this happens with. Your y-intercept becomes something that doesn't really make sense. Well, what we're going to do is cheese it a little bit. And again, this is the way that I handle things, just to make life a little bit easier for my students. So what we're going to do when we check, we think through this, okay, this doesn't really make any sense. So I'm going to change my math model. To what does make sense. It does make sense that the weight here would be 0. In this case, this is pretty darn close to being 0. So I feel pretty comfortable going ahead and changing that to just be 0. Okay. Other teachers have different methods of how they handle weird y-intercepts dealing with the error. For me, we just think about what we want to change it to or what we need to change it to. Usually, we would want to change it to 0 if we want to change it at all. There are times where it's okay to not have a y-intercept of 0. For example, our very first one, it made sense that this y-intercept was not 0. We're okay with that, right? If a baby's born, it has weight already. And that's okay. But down here, this doesn't really make sense for the y-intercept to be something other than 0. So we want to change it to 0. Now, as a quick aside, a quick last thing. If we have a graph, I'm just going to sketch it in here. We're not going to go super in depth. I'm not going to throw any numbers in or anything. If we have a graph and we have a negative slope, does that really change anything that we have there? No, it's not going to change things the way we handle things. The only difference will be, like, for example, let's say that this graph had a negative slope. So just imagine in your head, we flip this graph so that it looks more something like this, but all the numbers stay the same. So actually, let me change the color just completely so we see something different there. So imagine it's this green line here instead of the red line for now. If we have this green line here and we have the same slope, well, this just becomes a negative slope. So a student will lose 0.7367 pounds for every centimeter they gain in height. And that's a weird example because that doesn't particularly make real physical sense. But basically, we just have to think about how that decreasing weight affects the way that we talk about our problem here. So something to keep in mind, we'll explore this more, especially in my classes. And maybe in another video, I'll make a follow-up where we'll talk about a negative slope there. But negative slopes are okay. And they don't really change anything. Let's add that note there. Change anything. There we go, a little smiley face. Cool. All right, so that is some basic information of how we can pull from graphs. The main two things that we're looking for from a graph is the slope And the Y-intercept, the slope, tells us the rate, how things are changing, the relationship. That's the big one. That's the really, really, really big one, is the slope, right? How much per everything, right? How many pounds per centimeter? How many pounds per week? How many dollars per night, right? Whatever that relationship is. Also, the Y-intercept, the starting point. When something is zero, when we start out, what's our value? What's our starting point? Those are the two big things in being able to understand those. And we get those both from our math model. Thank you so much for taking the time to do physics with me today. I hope you have a wonderful rest of the day, and I hope to see you soon.